Let's jump right in. If you've ever stared at a complex engineering system and thought, how on earth do they predict what this thing is going to do before they even build it? Well, you're in exactly the right place. Today we're taking a really fascinating journey. We're going to transition from abstract system concepts to some incredibly simple, elegant mathematical solutions.
All right, so building on our previous explainer, you might remember we laid down some groundwork with three absolutely crucial system properties: linearity, causality, and time invariance. But let's be real, concepts alone just aren't going to cut it if we actually want to analyze real-world tech. We've got to translate this into math. So our main goal today is to mathematically describe a typical system block, let's call it S, by figuring out exactly how our input signal, U of t, morphs into our output signal, Y of t. We need solid equations to actually predict how this thing behaves.
So, how do we actually write that down? Well, the most natural way to describe a continuous time, linear time-invariant system is by using a differential equation with constant coefficients. Now, hearing that, it might seem like a rather intimidating equation at first glance. But honestly, it's actually quite beautiful once you break it down. All it's doing is setting the sum of the output's time derivatives, that's the left side, equal to the sum of the input's time derivatives on the right side. It's basically the engine of the system, literally the fundamental mathematical link between input and output.
Okay, let's just slow down for a quick second and actually define these variables so we're all on the exact same page. Breaking it down, it's pretty straightforward. U of t is our input signal, and Y of t is our output signal. And what about those A and B terms? Those are just our constant coefficients. A handles the output side, B handles the input side. And finally, the letters N and M simply represent the highest derivative orders for the output and the input.
And understanding these pieces brilliantly illustrates how all these specific terms link together to define the system's dynamics. But wait, there is a super important rule hiding in these variables, specifically for causal systems. For any real-world causal system, which just means a system where the output absolutely cannot depend on future inputs, the highest derivative order of the output, n, generally has to be greater than or equal to a highest derivative order of the input, m. Or, to put it simply, the effect literally cannot precede the cause. Makes sense, right?
But here's the catch. Here's the complication. While differential equations are totally the most natural way to describe things in the time domain, working with complex derivatives and integrals, well, it gets mathematically messy. It's just tough to manipulate. We need a bridge. We basically need a way to escape this time domain, which is full of tricky calculus, and teleport to a completely different domain where those exact same operations magically turn into simple, basic arithmetic. Think multiplication and division.
Enter the Laplace transform. This is an incredibly powerful mathematical tool that does exactly that. It teleports our time function s of t into a completely new space. We call this the Laplace domain, and it revolves around a complex frequency variable called p, which is defined as sigma plus j times omega. By taking the integral from 0 to infinity of our time function multiplied by e to the negative pt, we completely shift our perspective. We're literally trading the messy t-axis of the time domain for the super clean complex p-plane of the Laplace domain.
Let's look at the most useful properties of this transform, because this is where it gets incredibly practical. First off, it perfectly maintains linearity, which is great, but the way it handles derivatives and integrals, it's just astonishing. Assuming zero initial conditions, a time derivative of a function simply becomes that original function multiplied by our complex variable p. And an integral? It literally just becomes division by p. Plus, we get these awesome bonuses like the initial and final value theorems, which let us predict the immediate and the long-term behavior of a system without even needing to fully solve the equations. How cool is that?
So if you remember one thing today, let it be this central idea. The Laplace transform turns differential equations into algebraic equations. I honestly cannot overstate how huge this is. It is the magic key that unlocks the whole thing, turning complex, frustrating calculus into basic, straightforward algebra. By dragging our system into the Laplace domain, we make our lives so much easier, and our analysis way, way faster.
Now, what's really interesting is the absolute clarity this gives us. Once we've transformed our messy differential equation over to the Laplace domain, and again, assuming zero initial conditions, we can do something amazing. We just take the ratio of the system's output, y of p, to its input, u of p, and boom, this gives us g of p, the transfer function. This one single function neatly packages up the entire dynamic behavior of our linear time-invariant system into one incredibly elegant rational fraction.
Now, thinking about the factored form of this transfer function, we can pick out two incredibly important sets of numbers. First, we have what we call the zeros. These are the specific values of our complex variable p that make the numerator exactly 0. Then we have the poles. These are the values of p that make the denominator 0. And why do these matter so much? Because together, these poles and zeros completely shape the dynamic behavior and the frequency response of the entire system. They essentially tell us exactly how the system is going to react to any given input.
And just like that, we have successfully leveled up from messy differential equations in the time domain to the elegant, algebraically simple transfer function in the Laplace domain. But hey, this is really just the beginning of the story. In future explainers, we're going to dive deep into exactly how these poles and zeros dictate a system's stability, its transient response, and its frequency behavior. So before you head out, if this explainer helped you out, please drop a like, leave your questions in the comments, and tell me which part of poles, zeros, or system stability do you want me to explain more deeply next. Keep learning, and I'll catch you in the next explainer.